How can you scrape 25 lakh results from a website like this?
कितने साल से पेपर चल रहा है, अचानक पहले ही साल ऐसा कैसा हो?
Without pointing any fingers, have you wondered why examination websites are usually fairly dumb? How can you build a truly trustless, cryptographically verifiable system such that no single individual, no group of individuals, no government can tamper the results? How can anyone verify that their rank is absolutely correct and there were indeed X number of people ahead of them in this examination? If there were grace marks given, how many people actually got grace marks? In this video, let's look at how I would design an examination website so that if you are one of the participants, you can verify your rank and ensure there were indeed X number of people ahead of you. With that context, let's get right into it. Alright, gambling websites have something called provably fair games. Centralized exchanges have something called proof of reserves. What is the equivalent for an examination website? Hi everyone, this video is going to take us through how can we build an examination website in a truly trustless fashion. It is not going to be something super dystopian. We are not going to create a decentralized examination website. We're trying to create something similar to what centralized exchanges do in the real world to prove that they actually have your money, and gambling websites do to prove that all of their games are fair and they aren't changing the outcome of a game based on the amount of money that you are betting. Thankfully, these are solved problems, and I've thought of a very similar architecture for an examination website where number one, you do conduct examinations in a mildly centralized fashion, but how can you avoid the challenges that have been coming right now, which is people feel like something shady has happened, but they can't really verify how many people were ahead of them. Was there paper leaks, cheating? Are the OMR sheets changed? Things like these. How can you prove that none of this has happened? How can you build a truly trustless examination website? Let's get right into it. Some simple prerequisites. If you want to understand this fairly well, you should know how the internet works. What is a server? What is a client? What is front end? What is back end? Some first principles thinking, by which I mean, basic logic, understanding what's happening, encryption, decryption when I try to explain, you're able to understand it fairly well. And lastly, basic Node.js, Python, C, C++, whatever language you're comfortable with. We'll be writing most of the code in Node.js, but you can fairly easily extrapolate it to, Python, C, C++. What will we be learning today? We'll understand about centralized versus decentralized systems. What is a trustless system? Encryption versus decryption, if you've heard of it, maybe it's different from hashing. Public and private keys and public key cryptography, a very important component if you're trying to build something like this. Key sharding and Shamir secrets, a very popularly used technique if you want to have multiple players in a cryptographic system that are able to sign a transaction. Time lock puzzles, we'll discuss this, won't really use this. And lastly, verifiable state machines. These are two references. The first one discusses time lock puzzles. The second one discusses verifiable state machines. Both are pretty interesting reads. Without any further ado, let's get right into it. Let's understand what is the current problem in an examination like this. All right, what's the current problem in conducting an examination? It's that both the parties could be lying. It's very hard to tell right now if a student is just frustrated and hence saying some cheating has happened this year, or grace marks have been given out unfairly, and the government on the other side is not able to prove it only gave out grace marks to, let's say, 1,000 students. The rest of the ranks are actually right, and if you got a rank of, let's say, 40,000, there were indeed 39,999 people that performed better than you in that 3-hour window. There is no way to verify who is right. That is exactly what we're trying to build. By the end of today's class, you should be able to build a system where anyone can come and prove that indeed there were X number of people who performed better than me in that 3-hour window. This is a solved problem. This is just coming into light very heavily right now, but a few years ago, very similar tussle happened between the government on one side and people on the other side, and Bitcoin was born out of it. Currencies are actually a much bigger issue than an examination. I'm not trying to downplay, what's happened, but at the same time, we are slowly inflating currencies and printing money out of thin air, and no one can track where that money is going, how much money are we printing, things like these. There's no authority that's able to, govern, okay, we should stop printing. The government just prints money out of thin air. This was something people realized a few years ago and built, blockchains altogether. Bitcoin was the very first blockchain that solved decentralized currencies. We won't be building a completely decentralized system or a blockchain of ourselves. That does not make sense for this use case. It won't get adopted. But ideally, if you want a 100% truly decentralized system or a truly trustless system, then you ideally have to build a blockchain of your own or deploy this as a smart contract. That's not very practical. So let's look at the approach that we are going to take. Before we start, all of this relies on the assumption, okay, this paper is going to happen digitally. If there are going to be OMR sheets, if there are going to be physical papers on which things are printed, then of course there are too many men in the middle or women in the middle to attack the problem and leak the papers out. So a very big assumption is that there are no physical sheets, there are no physical papers, everything happens digitally throughout. Let's look at the current problems, even for a completely digital paper. IIT JEE currently happens digitally. These problems exist there as well. They of course exist in an examination like NEET, where questions are happening on a physical piece of paper and the answers are being filled on a physical OMR sheet. Alright, I've divided this into 3 phases. The things that can go wrong in the pre-examination phase, that's before the contest has even started, during an examination, and after the examination has ended. In the pre-exam phase, the biggest challenge that can come, the biggest place where you need to build trust is that the paper cannot get leaked. There are a bunch of attack vectors here. Attack vector number 1 is that the problem setter, the teacher itself, leaks the paper to one of their relatives or otherwise. That's of course not fixable. But how can you minimize the blast radius in case a teacher does think of, leaking the paper to one of their relatives? What if the database where the questions are stored gets hacked? NEET uses a simple centralized database on, a cloud like Azure or Microsoft. What if an engineer at Microsoft, let's say, is, able to read through all the problems? That cannot happen. Microsoft is a very big company. There's a very low probability of, an engineer at that company being able to read through the database. But we're trying to build a truly trustless system. That means we can't even trust Microsoft. If there is a centralized database where data is getting stored, it should not be stored in plain text. How do we fix this? We'll discuss this very soon. During the examination, let's say all of these are fine and somehow papers weren't leaked. During the examinations, the problem that can happen is number 1, your OMRs/answers can be changed later on. During the examination, there is a 3-hour window. You wrote a certain set of answers over there. What ensures anything that you put there during the 3-hour window is what evaluated your result, and that no one changed your OMR sheet or in a digital paper. Somehow the database wasn't changed with a new entry added for a problem solved by you, or your rank was modified to go up by a lot. Cheating, unfortunately, there's nothing you can do about cheating. Even like the best systems out there, if there is someone right next to me and I'm able to see their screen, I can copy. You can't fix this. Lastly, after the examination, this is the most critical bit here. This is where a bunch of problems happened this year. Number 1, results aren't given out immediately. This isn't necessarily a trust problem, but if you're doing a completely digital paper, it shouldn't take you, more than 5 minutes to calculate the result for all 25 lakh students. You should be able to immediately give it out. People getting grace marks and this data not being public. This has been the biggest problem this year. The government or, the testing agencies didn't even release the fact that, there were grace marks given. If this was, a truly trustless system, people would have been able to verify. Ideally, this person should get a 640. How did they get a 720? Where did the extra 80 marks come from? So how can you verify that there have been grace marks, extra marks, something, on top of what this user's performance was that was given to a certain student? Ranks and marks can be modified. Now, this is just pure speculation that people have made this year that, a lot of ranks were being bought off or, someone's relative got a better rank because, some entry was changed somewhere that beat the OMR sheet that was modified. or, the rank that was just changed in a database. All of these are speculations. None of this, it could be true, it could not be true. Unfortunately, this isn't a truly trustless system. The government will not make the data public ever. And hence, you can't really verify this. There is no way to verify my rank / the fact that X number of people were actually ahead of me. What do I need to prove by the end? If I have a rank of 600, I somehow need to be able to look at something and, verify if 599 people indeed performed better than me in that 3-hour window. How can you prove this so that there are no questions asked? There is no party that can come out and say, okay, my rank has been modified. And lastly, privacy issues because you can't scrape the data. This isn't really a problem. This is just the fact that, whoever is writing these systems is a bad engineer, hasn't covered a bunch of use cases or edge cases. All the data can be scraped. That's a privacy issue. You can literally find the result of any user, their parents' name, their address, things like these. And how many marks they got, their OMR sheet is also leakable. So, you can literally copy over the database of NEET if you want, including everyone's OMR sheets, and, run your own evaluation on top of it if you want. It's a good thing. I mean, in hindsight, this is great. Okay, you can actually verify the whole thing. It's like they've open sourced all the data, but they haven't done it intentionally. It's just that their systems are so bad that, there are very easy ways to scrape all the data and, create a copy of it locally. This needs to be fixed. If this is not fixed, it needs to be advertised this way. The NTA or whatever the agency is should publicly tell we are going to make your results public, because that's more or less exactly what has happened. Web2 solution. The first solution, that I'm just going to discuss right now is, if you don't involve cryptography over here, what all problems can you solve if you are purely sticking to how websites are usually built? Most websites are built on trust. If you are going into netbanking.hdfcbank.com, you trust them. If you send someone money, the money reaches the other side, gets debited from your account. Same happens for Facebook. If you send someone a friend request, you trust that the friend request reaches the other place. If you send someone a message and Facebook says your data is encrypted, you trust them, my data might be encrypted. But since, we don't really care about whether or not the data is encrypted on WhatsApp, on Facebook, you let it go. People aren't letting things go here. If you build a purely Web2 system, a bunch of these problems you cannot solve. For example, paper getting leaked, or the database where, your data is stored getting hacked, or the engineer at Microsoft looking at your database is something you cannot solve unless you bring some encryption into the picture. You bring some cryptography into the picture. You can't solve the first problem. Similarly, the second problem is not solvable. Cheating is generally not solvable, but your answers can be changed later on, cannot be solved if you have a simple Web2 unencrypted database, because an engineer at Microsoft, or, an engineer at the company that's handling the NTA website or whatever website is hosting the questions can go in there and make a database entry later on, solve a few questions for one of their relatives. So this cannot be solved again in a Web2 fashion. You need something extra, some cryptography on top. After the examination, results being given out immediately, that is one problem that can be solved even in the Web2 world. If you're building a simple website, after the exam has ended, just aggregate the results of all the users, find their marks, and rank them from top to bottom. This can be solved even without any decentralization, any cryptography, and privacy issues, because you can scrape the data. There are fairly simple things you have to do to make sure people can't scrape, people cannot do brute force attacks. Add a captcha on it, send the user an OTP, IP rate limit people. Just make sure they can't, send you infinite requests and brute force your database to find, the results of every user and the OMR sheet of every user. If you use some cryptography and you build a mildly decentralized solution, again, we're not building an on-chain examination solver. We are building a centralized system with some jazz on top. If you do that, you can solve all these problems, minus the cheating, of course. Can't really fix cheating, but everything else can be solved, with the help of some cryptography and decentralization. Let's look at all three of these phases one by one and see how we can solve these problems. To recap, what are we trying to build? We're trying to build an examination website in a truly trustless fashion. Currently, examinations are a high trust system. You trust the central authority to play by the rules. Most probably they are. We need transparency and not a single entity owning this examination. We need to build a truly trustless system. How can you build something like this? Let's get right into it. let's go through the pre-examination phase first and understand how can we solve both of these problems with some very minimal cryptography. This is how problems should be set ideally. If you want to build a system where there isn't a single teacher who owns/knows all the problems, you'll probably create small groups of teachers in various cities that don't know each other at all. That'll be creating the problem set for NEET this year. Let's say this is this central AWS database where you want to eventually store all the problems. And the first set of teachers in Tamil Nadu, let's say, submitted 100 problems over here. These 100 problems exist in your centralized database on AWS. Then in a day or two, the folks at Bangalore made their submission. And lastly, a bunch of folks from Delhi, a bunch of other cities submitted some problems that might come in NEET this year. Or let's say in this case, that will come. Let's say NEET has 500 problems or IIT has 500 problems. You've divided them into 5 disjoint groups that don't know each other. Why have we done this? This is purely done so that, if there is one person here who's an imposter who shares the problem to their relatives on the internet, only 1/5 of the paper gets leaked and, not the complete paper is leaked. There is no single person who has access to the complete problem set before the examination. That is what you would think would happen. Okay, only these people know 100 questions. These people know 100 questions. These people know 100 questions. 2 other entities know 100 questions. But if you store all of this data in a database, there might be someone who has access to all 500 problems. Whoever is the administrator of this database, if this is an AWS machine, then maybe some employee at Amazon can read through these problems and, leak the paper even before it is released at 9 a.m. AWS is centralized. This is dystopian. This won't happen. Amazon is a very big company, very low probability an engineer over there has access to your database. But, the consultancy that might be writing this, whoever has written the NTA website, whoever has written the examination website, an engineer there might have access to the database through some weird security holes. A hacker might be able to reach this database if your website isn't protected correctly. So, an AWS engineer could steal the question set. An engineer from the team that's creating the website could steal it. Or, a hacker could steal this data. If you put this data in a centralized database, consider it to be open to the world. Whenever you store data in a centralized database, almost assume this data is, open to the world, can be modified and can be, read by some engineer somewhere. It's on a machine. Machine is owned by Amazon. Amazon can read through it. Only people who set the problem should ideally know the problems. The blast radius of attack, in case there is an attack, it should only happen because person 1, person 2 or person 3 over here leaked the problem and 100 problems are now completely open. If that does happen, you can create some incentive for people to report it. And that way, the Tamil Nadu center has done a problem. Next year, the Tamil Nadu center is completely blacklisted. This is one approach of, trying to minimize the impact of leaking. What are we doing? We are number one, dividing the problem set into various regions so that in case a teacher does go rogue, only a certain set of problems are leaked. If this happens before the examination, you can remove these problems from the problem set. If this does not come out, if they share it with a relative, unfortunately, there's nothing you can do. If this person 1 has a brother-in-law who's giving examination this year and they leak the paper to them, they leak the paper to them. Only people who set the problem should know the problems. They should be max the people who can leak the paper, no one else. No one at Amazon should be able to leak the paper. How can you prevent that? Can you think about it? I discussed this a little bit in the third slide where I was sharing the things that we learn. You can use encryption. What is encryption? If this is your problem statement, let's say a very simple problem is something that a doctor is trying to set or an engineer at IIT is trying to set for this year's IIT JEE. This is what the problem looks like. Before it reaches the database, it should be encrypted. What does encryption mean? It means you take a certain password, a certain secret that only those professors know, and take the problem and encrypt it using this secret. What does encryption mean? It means it will spit out some gibberish and you cannot convert this gibberish back to the original problem unless you have this encryption key. I repeat, Encryption is the process of taking some standard text, a message, and as the name suggests, encrypting it into a certain fashion, into a certain new string. And it's very hard, or not hard, it's impossible for you to get back the original string unless you have this encryption key. This encryption key is something that the engineers at IT, doctors at a specific hospital should keep very safe. If they leak this, it is equivalent to them leaking the problems on the internet. What is decryption by the same logic? Okay, if you do have this gibberish and you have the encryption key using which you had encrypted the problem, you can get the original problem that the problem setters had set. So what have we learned? We've learned about encryption. We'll be reading the code that lets you encrypt very soon. But as the name suggests, it lets you take some plain text data and convert it into some gibberish using an encryption key. How does this come into the picture for us? It comes into the picture because when the problem setters are done setting the problem, if this is one problem, but let's say they set 100 problems, they can encrypt all 100 problems using their encryption key. Let's say the encryption key the folks at IIT Bombay chooses IIT Bombay rocks 3123, something like that. The professors over here can decide what the encryption key is, and they can encrypt all the problems before sending it over to the AWS server. But you can literally store this information anywhere. It's a trustless system. You do not trust AWS. You can just post it on a public blockchain. You can post this data literally anywhere. You can make this data public. This encrypted problem that you see on the right, this problem that has been set for this year's IIT JEE, can actually be publicly released even before the examination because it has been encrypted using this encryption key. As long as the professors at IIT, problem setters keep this encryption key safe, should be fine. The problems will remain on a public platform, but you can't really tell what the problem is by looking at it. It's pure gibberish if you look at it. Now, if the professors at Tamil Nadu do release the encryption key by mistake or intentionally, that is equivalent to them just, releasing all of these questions. So, you would hold them accountable just like you would hold them accountable if they released this. If either one of them they release, it means this specific center has done something shady this year. You blacklist them for next year to set problems. This solves the first problem. We are now storing data like this. It doesn't matter if it's stored in an AWS server. You can also post it on a public platform. These are the problems for this year. You cannot look at them and tell anything. You just know there is some gibberish problem statement and 4 gibberish answers that you can look at. All the problems that have been submitted by all the centers for that year are first encrypted before you send them. Each center has their own encryption key that they're going to keep safe. If they leak the encryption key or leak the papers, that means the center is not being ethical this year. This solves the problem of papers getting leaked. This also solves the problem. What if the database where the questions are stored is hacked? If the database is hacked, it's fine. All the data is encrypted. You can literally just store this data on chain publicly. Anyone can look at it. Paper cannot get leaked unless, of course, one of these parties itself leaks it, which, is just an ethical issue on the problem setter's side. There's nothing you can do about that. If a problem setter itself is leaking the problem, then their incentives aren't aligned and, they're not doing their job correctly. Why store it publicly is another question you might ask. Harkirat, why are you saying you can store it on an AWS server? But you can also store it on a blockchain only so that anyone can look at it. Store it on an open server. Store it on something called IPFS. What even is IPFS? All 3 of these options state, store this big ledger of 100 problems that you have. Store them anywhere, doesn't matter. Put it on a website for everyone to look at. Why? Because number 1, you can verify after the contest the questions weren't changed at the last moment. If this is the 100 or 1000 set of problems that have been set for NEET this year, they've been set 1 month in advance. No teacher is coming at the last moment and changing the problems because they shared them with their relatives or something like that. You can be sure that the problem set was logged 1 month before the exam actually happened. And it is fair to everyone. No one has any extra information. If you store it on an AWS server, then an AWS engineer might have some extra information by looking at this encrypted data. But if you literally store it publicly, then anyone can look at this before the examination and they will get no information. If there is some information, everyone gets access to it fairly. That is how you would build the very first pre-contest phase. It gets rid of both the problems that exist in the pre-contest phase. To recap, what did we do? This is the architecture that we followed. Okay, whenever you divide the problem set into various centers, let's say 20 centers, each center sets 50 problems, and all these problems are encrypted before they reach the centralized database. Eventually, the centralized database looks something like this. It has all the questions, but they're encrypted so no one can understand them at all. Harkirat, how do they get decrypted? How does the person at 9 a.m. on the day of the examination actually see the real problems? Is something we'll discuss in the next section. This covers the first checkpoint, which is before the contest. Let's get into during the contest. What are the problems that exist during a contest? How can you solve those problems? All right, before we proceed, let me also keep checkpointing you with the code. All the code for this specific video will be present on GitHub. There are a few sections. The section that we're looking at right now is one examiner problem encryptor. Basically stores the code of how examiners can convert their problem statement into some encrypted text that they eventually send to a server. Now, of course, the examiners would see this on a website. This is just a trimmed down version of it. What might happen on the backend? Let's say this is a problem statement that the user wants to encrypt. The statement is what is 2 plus 2, and these are the 4 options. How can you encrypt it, and how can an end user eventually decrypt it in case they do have the key? Crypto is a library, as the name suggests, in Node.js that lets you do cryptography. What are we trying to do? We're trying to encrypt these 5 things before we send them somewhere. I've defined 2 functions. The very first function is called encrypt. It takes 3 inputs: the text that you're trying to encrypt, the encryption key using which you're trying to encrypt, and lastly, an IV, something known as a initialization vector. The goal of this third argument is just to make sure you are given some text and given a key. If the IV is different, you get different outputs every time. It just makes it less guessable. What is the goal of this third argument here? To randomize the final outcome that comes for the same text and the same key. I repeat, if the text that you're trying to encrypt, let's say, is what is 2 plus 2, and the key that you're trying to encrypt it with is IITB 2023 secret, then to make sure that the output comes out is not the same if you call this function twice. If I call this function twice, you will get the same output unless you have a new initialization vector every time. This is like a seed, a way to make sure for the same key and the same secret, you can have different encrypted outputs. So that, why would you want to do this? Just for security purposes. If someone knows, for these 2 inputs, this is the output, then if you give them the same output again, I repeat, if you give them the same output again, then they will remember that last time though I remember for this specific encrypted key, the original key was this. So if you get the same output again, they'll be able to guess the original key, which is why the concept of salting or seeding exists when you're trying to encrypt data. This can just be a random string that you select or random set of bytes that you select. This is the text that you're encrypting. This is the secret that you're encrypting with. What does the function do? It defines an algorithm that you're using to encrypt. There are various encryption algorithms that exist. What is the property of an encryption algorithm? Given an input, the output that comes out is pure gibberish, and you cannot get the input back unless you have the key that the encryption algorithm used to encrypt it. We create this cipher variable, which is nothing but crypto.create cipher IV. It takes the algorithm as the input, the key as the input, and the initialization vector as the input. Then we update the cipher. This basically means think of it like creating a lock. And then you add some values to the lock. For example, the value that we're adding here is the text that the user is trying to encrypt. This text is input in UTF-8. What is UTF-8, 𝗥𝗲𝗄𝗃? Simple plain text English that you write. For example, what is 2 plus 2? Anything that lies in the English language between, in ASCII characters is what's called UTF-8. What is hex, 𝗥𝗲𝗄𝗃? Hex is our final output, which is going to be hexadecimal. What are hexadecimal strings? Strings that have, anything from A, B, C, D, E, F, G, H, I, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0. So yeah, it does have 0 as well. The final string that pops out has, just these 16 characters, hence the word hexadecimal. This is the format in which we want the final gibberish to be spit out in. Finally, we call cipher.final hex because hexadecimal is what we're trying to convert the string in and return this encrypted value from this variable. And just how this encrypt function takes a text, key, and IV as an input and encrypts the text. There is a decrypt function which takes the encrypted string and the key and the initialization vector as an input and pretty much runs the opposite of what we've written over here to decrypt the string. You can also take both of these as complete black boxes. A lot of times you just Google to get how do I encrypt a string from one format to another, given the algorithm that you want to use. We are using AES 256. You can use a different algorithm to encrypt the strings. Given we have these two black box functions, what are we doing over here? We're initializing the key. Now the key can be a string that looks like this, IIT Bombay Secret 2023, which you can always convert to, a bunch of bytes, which means zeros and ones. Or you can simply just use crypto.random bytes, which is what we're doing here, to generate 32 random bytes. That will be our key that we're signing everything with. And we similarly generate an initialization vector, which is also a random bytes, 16 bytes that we're randomly selecting, which are going to be the IV for this specific iteration. Then we simply call encrypt 5 times, once for the problem statement and 4 times, once for each option. We print all the encrypted options. Then we call the decrypt function with the same key and the same initialization vector with the encrypted problem, the encrypted option 1, encrypted option 2, so on and so forth. And lastly, print everything decrypted. The goal of this file is to show you how does encryption happen, how does given a string and you can generate a random initialization vector, how can you encrypt a bunch of problems, and given you have an encrypted string, how can you decrypt that string back. If you look at the results, if I do node index.js over here, you will see it says the problem statement in the encrypted format looks like this. As you can see, you cannot tell that this original string was what is 2 plus 2. Option 1 looks like this. You cannot tell the original string was 4, so on and so forth. The decrypted strings indeed look like the original, which means yes, we were able to encrypt the strings into some gibberish format. We were able to decrypt them back to the original text. This is a brief of how you can encrypt strings in Node.js. The same logic exists, as long as you know the algorithm that you're using to encrypt the string, you can encrypt it in Python, C, C++, Node.js, Golang, whatever language you want. Should I write these myself, 𝗥𝗲𝗄𝗃? No. Any language that you're working with, you will just use, hopefully, a well-orated library, which gives you all of these encryptions out of the box. You don't have to, write the whole encryption algorithm yourself. You can if you want to, but that's a little too much of, over-engineering for this problem. Given that you understand the code a little bit, now let's try to dive into what happens during the context. Before the context, we understand everyone encrypts the problems, put them on a database. During the context, what are the problems that exist? Number 1, how do questions become open at 9 a.m.? This is a new problem that came. 𝗥𝗲𝗄𝗃, you encrypted the whole database. The whole database, doesn't matter if it's centralized or decentralized. All the problems are encrypted. How do you decrypt these problems on the day of? If it is 9 a.m. on the examination day, how do all of these get decrypted? That's the first problem. And what is the second problem? how can you be sure that all the submissions that you see were indeed made by the user during the contest and not added later? How can you be sure no one's modifying the database after the contest? It is indeed in that 3-hour window that they made these set of submissions. Let's understand both of these problems one by one. Here comes something interesting to learn, or something that took me years to learn, if I'm being honest. Two approaches to solve this specific problem. What are we trying to solve? Here, the teachers have created this very encrypted database, and we need to make sure this becomes public at 9 a.m. There's a certain time at which we want either the teachers to release their encryption key or the teachers to just release the problems. How can you have a certain timestamp at which all of these questions become publicly available? There are two approaches you can take here: time lock puzzles or trusted agents with Shamir Secrets. The first approach is weird. Don't take it. I'm going to discuss it, but there are some shortcomings in it. Shamir Secrets is the ideal way to go here. Time lock puzzles, as the name suggests, are basically puzzles that you can lock for a certain amount of time. If I want to write a message right now and encrypt it for the next 50 years, this message should only be available in 2074, 24th April 2074, let's say. I want this message, it's like a time capsule. I want to create a message and encrypt it such that it can only be decrypted in 50 years from now. If there is an algorithm that lets you do this, then I can just run that algorithm for the encryption key. I'll take the encryption key and I will time lock it. I want it logged for the next 30 days and 20 hours, which is exactly when 9 a.m. will come on that examination day, and this encryption key will become public. Question is, can you do this? Can you encrypt something? Can you time lock something such that it becomes available in, X number of hours? And the answer is yes. Here is a nice paper that takes you through what are time lock puzzles and how do you create one. The only problem is they depend a little bit on how computers become faster and faster over time. It's very hard for you to say, okay, this problem will be solved in the next 50 years. You can say this problem will be solved in, 100,000 iterations or 1,000,000 iterations. Then the time that it takes for an iteration to happen might go down as time goes by, as years goes by, as machines become stronger. So, it's very hard for you to pinpoint, okay, this key will become public exactly at 9 a.m. on a certain morning. It might become public on 8 a.m., which will create all havoc if that happens. All problems are public. If the encryption key becomes public, students are standing right outside the center and then are able to read all the problems. That's bad. Hence, this is a bad approach. I've written the code for it. If you want, you can actually look at it. The second folder that you see over here, time lock puzzles, imports this library called CryptoPuzzle, which does an implementation of a time lock puzzle. One thing about time lock puzzles is you can't make it faster by parallelizing. You cannot parallelly solve this problem. If I have a 16-core machine, doesn't mean I can run this 16 times faster than a friend who has a very cheap machine. This puzzle can only be solved on a single core of a machine, which is why if you set a certain time, let's say a year, there's a high probability it will get solved in a year. I can't just get all of my friends' laptop and parallelize solving this puzzle. This puzzle can only be solved in a single core of a machine, which is why you can sort of say it has been logged for some time. Again, it's not logged for some time. It's actually logged for some compute units, and the number of times, the number of iterations that you can do, the number of compute units that you can consume in a second might go up over time as hardware gets stronger. And hence you can't really say, okay, this can be solved in exactly 50 years and 20 hours and 5 minutes. It might be somewhere around that time, but not exactly that. Let's look at this implementation. What does it do? It calls a main function, which creates a puzzle where it says the number of operations per second, at least right now on a Mac M1 machine, are these many. A Mac M1 machine can do these many operations per second. And I want the duration to be 10 seconds. I want this specific message of mine gets logged for 10 seconds. Doesn't matter where this specific puzzle is solved. It should take around 10 seconds to be solved, as long as that machine is this much fast. Now if that machine is twice as fast, then of course it will take half the time for it to be solved on that machine. Or what if you use a supercomputer? Again, as I said, doesn't matter if you have 40 cores, 100 cores, 200 cores. This can be solved on a single core. So the number of operations on that specific supercomputer might be this. It won't be 100 times better or 1,000 times better. It'll just be like 20-30% better if at all. Let's try to see if this actually does what it says it does. If I run npm run start, it starts the puzzle. Then as you can see, it's stuck for a while. It will stay like this for the next 10 seconds. It's basically stuck on this line right here. It's trying to solve the problem. It is actually, running a mathematical solution, trying to solve it. And eventually after 10 seconds, it does solve it and logs the original string. Let me change this to 5 seconds. And let's see if that does take the time that it takes for it to be decrypted down to 5 seconds. 1, 2, 3, 4, 5. I think we're down to 5 seconds here. What does npm run start do? It simply starts it. I should have done npm run dev. Let me do npm run dev. And now it should take hopefully 5 seconds. 1, 2, 3, 4, 5. And the puzzle is solved. There you go. Took like 5 seconds. If I increase this to 50 seconds, it will take 50 seconds. You get the idea. But this isn't a good solution. It might open up the problem an hour before the actual contest, which is something we don't want. And hence, but this is an elegant solution though. Like time lock puzzles, if they were literally time logged, they aren't time logged, they're actually operational logged, the number of operations that you can do to solve that specific puzzle. But if they were time logged, then this is a great use case to build a lot of things. A time capsule is a great thing. If you want to do crypto releases to another person at some specific timestamps or durations, you can use something like this. But not a good solution for this specific problem. What is the problem that we're solving again? Okay, at 9 a.m. this database should get decrypted. Everyone should be able to read all the problems, or maybe not everyone, all the students should be able to read all the problems. Before that, no one should be able to read the problem. No AWS server should have all the problems in plain text before 9 a.m. At 9 a.m. these should get converted, or somewhere around 9 a.m., 8:59 a.m., 9:01 a.m. all of these should get converted to plain text. The second approach here is the Guardian approach. This also exists in this specific paper if you go through it. The Guardian approach says, whenever a center that's creating the problems, Tamil Nadu, Delhi, whenever a hospital is, let's say, creating a problems, they create this encryption key, right? They should break this encryption key into slices. Let's say they break this into 3 slices. INCRY, that's the first slice. They send it to NTA, one very big entity in India. This is one guardian. This is someone you trust, an authority that you sort of trust. Then the second slice over here goes to the Delhi government. The third slice, let's say, goes to the Punjab government. You find many such guardians, let's say 20 such mildly trusted guardians that you sort of know they probably won't do bad things. You're still trying to decentralize risk. You're still trying to find opposing parties. You're trying to find various, state governments. You might find private companies as well. The biggest private companies in India might also be a good option to, have as guardians over here. And you give all of them some part of your key. You don't give any of them your whole key. If you give them your whole key, then, people at NTA can decrypt the database. But we want here, none of these can independently decrypt the database. Of course, if all of them go rogue, if all of these guys meet one day, an employee at NTA, an employee at Delhi government, and an employee at Punjab government, they'll all be able to add these 3 strings and create encryption, which is the key that is being used, and then they'll be able to decode the database. The goal is whatever guardians you choose, number one, you have a lot of them. You have like 20 guardians, let's say, and only if 18 of those guardians, let's say, meet each other, or 15 of those guardians, you can decide what that number is. If 15 of them meet and try to rat the system out, then of course they can decode all the problems, but it's sufficiently decentralized. If all of these are fairly opposing parties, they don't have any incentive to join together, they'll most probably not meet each other and try to find what this original encryption key was until the day of. Until the final day, they will not try to meet and do something shady. On the exam day, these parties somehow meet and join their keys, and the encryption key is finally made public. If this encryption key is public for a center, then the problems of that center can be decrypted. You can get the original plain text problems of that specific center. What is the approach again? Whenever the problem is being set, after it's reached the database, you break your encryption key and send it to various guardians. On the final day, the guardians somehow join their keys, make it public, or simply hit the public database and decrypt all the keys and decrypt all the problems, so that all the students can read the problems. This is what happens on the day of at 9 a.m. This table is taken that has encrypted entries, and using the encryption key that these guardians were somehow able to join at 9 a.m., the original problems are retrieved, and everyone can now finally see the original problems and start to solve them. But this is an ideal approach for multiple reasons. You should use something else. Specifically, Shamir Secrets is something that solves this problem more elegantly. What is the problem? We want to shard a specific secret. We want to break a secret into various parts. But this is not the right way to break it. Ki yaar, first 4 letters isko de do, next 4 letters you should give to this guy, last 4 letters give to this guy. This is not an elegant approach. I'll share why. Shamir Secret solves this exact problem. If you ever want to decentralize, give out a secret to various people such that if a few people meet, they can recreate the secret, Shamir Secret lets you do exactly that. Shamir Secret sharing is an effective secret sharing algorithm for distributing private information like the secret among a group. What do I want to do? I want to distribute the private information that I have among a group. Let's look at what's the problem in breaking the original encryption string into just 3 parts. Let's say the first part goes to the first guardian, second part goes to the second guardian, and third part goes to the third guardian. The problem here is that the number of guesses that you need to guess the original encryption string is really high. You need 26 to the power 14 possibilities, let's say. If you calculate all the permutations and combinations you have to go through to guess this encryption key, if there are 14 letters over here and 26 possibilities in every letter, you have to go through 26 to the power 14 iterations to guess it, which is a really high number. You'll not be able to guess it. But if I break this down into slices, then the first slice already has ENCYR. It knows the first 5 letters. It only has to guess 26 to the power 9 letters, which is much less than 26 to the power 14. So you make the problem easier for this guardian to solve in case you give them a certain portion of the string. This is why you should not be breaking this into, let's say, 3 parts over here and giving the first part to the first guardian. They'll be able to guess the problem or the rest of the string fairly easily. This is where Shamir Secret come into the picture. They let you shard or break an original string, let's say this encryption key, into various parts such that all the 3 parts give no extra information. If there are 26 to the power 14 guesses you have to do here, there are 26 to the power 14 guesses that you have to do here as well. It does not give you any extra information. You cannot, just because it gave you a string like this is complete gibberish. You cannot guess the original string with any higher probability given this gibberish that you got from Shamir's. So what does Shamir Secrets let you do? They let you break the original key. They let you shard the original key into various sub keys such that each user has no extra information given these keys. But if these 3 users do join together, they can again create the original encryption key. In fact, if you create a 2x3 Shamir Secret, what does 2x3 Shamir Secret means? It means just 2 people are enough. If these 2 people meet, they can create the original string. Or if these 2 people meet, they can create the original string. Or if these 2 people meet, they can also create the original string. Of course, if all 3 of them meet, then they can also create the original string. But you decide these thresholds. Yeah, I want 20 guardians total, and if 15 of them meet, good to go. That means you can create the original encryption key. Any of these 2, in our case, if they meet, they can create the original encryption key. What should this number be? Depends on you. How decentralized you want your system to be. If you want your system to be extremely decentralized, you might have 50 guardians and 49 of them have to sign to be able to see the original string. Or if you want it to be slightly less decentralized, in our case, we want to make sure at 9 a.m. paper becomes available. If the government of Punjab has a electrical outage and they're not able to join, people should be able to give their examinations still. And hence, you can have 20 guardians and if 15 of them sign, you're good to go. You should reveal the encryption key. Hence, we'll create like a 15 by 20 Shamir secret in our approach. And you can decide what these numbers are based on how decentralized you want your system to be. A question you might have is, how does Shamir Secrets work? What is this fancy technology that lets you break an encryption key into various parts such that if two of those parts meet, you can create the original string? Let's look at the code first. This is actually a fairly interesting code to look at. The 3-examiner Shamir generation. If you look at this file, fairly small file, nothing too big here. I use the Shamir secret sharing library. I create a uint array or a buffer from an original string that I'm trying to encrypt. This is the string that I'm trying to encrypt. This is this thing on the left. Then I say sss.split secret shares 3 threshold 2. What do I say? I want to create 3 shares. I want to create this, and this, 3 shares, and my threshold is 2. If 2 of them meet, they should be able to generate the original string. Smaller shares is shares.slice 0,2. What do I say? If the shares array will of course have all 3 of these strings. The first string, let's say, is this. The second secret, let's say, is this. And the third secret is this. Shares.slice 0,2 creates an array with just the first 2 elements. Something like this. That way, even if I take just the first 2 possibilities, the first 2 Shamir shards, and try to recover by calling sss.combine, SSS, which is the library, .combine just these 2 elements. If I just combine using these 2 elements, I can still recover the string. If I log recovered over here, you will see it logs encryption key. If I try to run this simple Node.js code, you will see it shows me the 3 Shamir shards that were created, and it was able to get back the original encryption key. If I make this 1, if I say, here a single person is going to try and decrypt the secret, they won't be able to. They get back some gibberish because our threshold is set to 2. If our threshold becomes 1, then of course they'll be able to decrypt the string. If our threshold is 3, then also we have to take, all 3 of these shares, and only then will we be able to get the original string. If I take all 3 of the shares, if all the 3 parties meet, considering threshold has become 3, then of course I'll be able to decrypt it. But if I, let's say, slice or get just the first 2 values, then I won't be able to decrypt the string. That is how Shamir secrets work. Fairly proven algorithm used very often in, exchanges, whenever you want distributed consensus, whenever you want distributed key generation or, distributed signing, Shamir secret is like a pretty popular approach. The question that you might have is, Harkiyat, how exactly do they work? How is it happening? You broke the string in such a weird way. If 2 of them meet, they can get the original string, but a single person cannot. If all 3 meet, then also they can get the original string, but there is no extra information over here. How exactly does a Shamir secret work? And it's actually fairly simple to understand. Let's look at this in context of numbers, and this numbers can easily be extrapolated back to strings. You can convert string to numbers, you can convert numbers to strings. Let's say the number that you're trying to encrypt is 400. This is the thing that you're trying to encrypt over here. What you can do is, you can say 400 is this point on a simple XY axis. 0,400 is the point that you're trying to encrypt, 400 being the Y coordinate of this specific point. Then just draw a random line, doesn't matter. Draw a line with a certain slope and start to pick points on this line. You have infinite number of points that you can choose from. start to pick points on this specific line. Let's say you pick one such point. That is your first Shamir secret that you can share with one person. Let's say you're trying to create a 2x3 Shamir secret. You're trying to share secrets with 3 people such that if 2 of them meet, they can get back the original point over here. This is the first Shamir secret. Let's say this is the second Shamir secret, 600,100. And lastly, this is the third Shamir secret that you create, 800,0. These are just 3 points on this specific line over here. If 2 of these people meet, let's say this guy and this guy meet, can they get back the original number? If this guy and this guy meet, you can just join these 2 numbers, right? And this line, when extrapolated back to the y-axis, will lead you to 0,400. These 2 people can get back the original number. Can that happen for these 2 people as well? If these 2 people meet, they can draw a line amongst each other, which if you extrapolate will reach this specific point. These 2 people can get the original secret that was being encrypted. And lastly, again, if you pick a third one, the other 2 possibilities, if these 2 people meet, or if all 3 of them meet, if you join these lines, it will eventually extrapolate to 0,400, where 400 was the thing that you were trying to encrypt. This is how Shamir secrets work. This can be extrapolated to 3x5 Shamir secrets, 5x10 Shamir secrets. In the end, you're trying to encrypt a certain text/number that can only be decrypted given a certain number of strings. If you had to do a 3x4 Shamir secret, then you'd probably have to convert this into a curve like this. If you had to do a 4x5 Shamir secret, it will become a more curvy curve, so on and so forth. If you've done basic algebra in school, it's fairly easy to understand. If you need 2 as the minimum number of things that you need to create a line, if you need 3, then you need to create a parabola, and keep going from there. That's how a Shamir secret works. Question is, how does it help us? How does it make sure at 9 a.m. how does it solve this problem right here? How do questions become open at 9 a.m.? And the answer is, during the problem setting phase, when let's say a center in Tamil Nadu is trying to set problems, after they encrypt the problems and send it over to, let's say, an AWS database, wherever they're sending it, they also take their encryption key and create Shamirs out of it and send them to, the NTA, Delhi government, Punjab government. These guys need to store these Shamir secret slices from all the centers securely. I repeat, if Tamil Nadu is a center and Tamil Nadu put a bunch of problems, they will also give the respective slices to each government, or like each state government, each guardian that you have, so that on D-Day, on the final day at 9 a.m., some of these guardians publish their Shamir secrets for all the centers, which once you combine, you can decrypt the actual problem. We are delegating the task of maintaining extremely trusted things to, extremely trusted organizations. We're not keeping them. You could also say, on the final day, Harkirat, the Tamil Nadu government or the Tamil Nadu problem setters would just release the encryption key, but you don't want to be dependent on them. This guy is not this is the problem setter. You don't want to be dependent on them to release their encryption key at 9 a.m. Also, this is a single person, a single entity. What if they're sleeping at 9 a.m. that day? This is why you create a bunch of guardians. The guardians, number one, keep these Shamir secret slices secure until the final day. At 9 a.m. on the final day, hopefully all of them make their Shamirs public. If not all of them, even if some of them make it public, and our threshold is low enough, let's say our threshold is 7/10, if 7 of these guardians make them public, you can regenerate the encryption key and make all the problems here public. Why is this good? Because only if a bunch of very big organizations work together at 9 a.m. will this data set become public exactly at 9 a.m. No person all around the world, other than of course the problem setters, know the exact problem set that the user is going to see. It's encrypted everywhere. Neither can an AWS engineer find that out, nor can an engineer at the consultancy that's creating the NTA website find out the exact problem set. Only if 7 of, let's say a Shamir threshold is 7, Only if 7 of these very big organizations are in bed with each other and, have some incentive to release the paper early or get the problem somehow early, that's the only case in which you'll be able to release the problems earlier than 9 a.m., which, you just make it more and more decentralized. You can have 20 organizations, 30 organizations. You can bring in private companies to make sure that this is sufficiently decentralized now. Unless all of these companies are working together to make the paper public earlier than the exact timeline over here, I think we should be fine. Even if some of them do make the data public earlier, you know who is this specific, organization that's trying to cheat the system or, making the data public earlier, and you can always, penalize them. In the end, there are like real incentives for these guardians. Every person who fills out an examination form pays like $1,000. You should be paying both the problem setters as well as, all the guardians over here. They should be incentivized in some way for, playing the game fairly and releasing everything at 9 a.m. That's how you solve this problem right here, making sure the problem becomes open at 9 a.m. What have we learned? We've learned about Shamir Secrets as the only big thing to learn over here. If you understand them, you can also, if you're building a gambling website or an exchange, your withdrawals usually go through either Shamir's or something else, which is called an MPC, multi-party communication. Out of scope for this video, but like great reads in case you ever want to build, a cryptocurrency exchange and you want to hold millions of dollars for other people. To make sure, no developer of yours can take out all the money and, just pay themselves all the cryptocurrency. You can use either Shamir's so that your secrets are distributed amongst various developers, various teams. So unless multiple developers are working with each other, they'll not be able to pull out all the money. Or you can use an MPC setup where, there'll be more than one guardian, usually like 5 to 6 people. If they all work together, the withdrawal will happen. Usually there's a very low probability of everyone being, on the dark side in a cryptocurrency team and, thinking of doing shady things like this. The other thing is, this is the biggest really problem to solve over here, which is how can you ensure that all the submissions that you see were indeed made by this user during the contest and not added later. One speculation that people have, which is, a fair speculation to have, is that, some guy's relative mama chacha taya changed their OMR or, is updating the database somehow. When the user submits a problem, how can you ensure, the final result that's coming out was a problem that indeed this user solved during those 3 hours? There is no person in AWS, there's no relative of this person in that company that's modifying the results, that's modifying the OMR of this user, modifying the submissions of this user after the contest has happened. If this problem is solved, every other problem is solved. This is the only other challenge that's left. Let's get into this next. All right, let's get into the most difficult, hard to decentralized, extremely needed part of building a system like this. How can you ensure that all the submissions that you see were indeed made by this user during the contest and not added later? How can you be sure that in the conventional world, their OMR wasn't tampered with later on? In the digital world, there's no one else who's updating the ranks of a user, updating the numbers of a user, adding grace marks, for example, or, just changing the submissions of a user. How can you be completely transparent? The ranks are based on submissions that were done during a 3-hour window. There are 2 approaches to this. The most obvious approach that comes to mind is, just create a blockchain. This is what blockchains do. You put data out for everyone to see. If there is some amount of BTC that you own, Bitcoin, Ethereum, Solana, it's on chain for people to look at. If you ever transact on it at a certain timestamp, anyone can look at that transaction throughout history. It's there forever. Why not do something similar, Harkirat? Why not start to create a smart contract and expect the students to write directly to the smart contract, call a function on the smart contract that, stores their submission on chain? This is a decent approach, but this won't work practically for a use case as big as NEET. Let's discuss why is that. Let's discuss blockchains first, and eventually we'll get into verifiable state machines, which is the right solution for this problem. A brief about blockchains. What exactly is a blockchain? As the name suggests, it is a bunch of what are called blocks. And if you chain them together, it becomes a blockchain. Harkirat, what does each block contain? Each block contains a bunch of transactions. Not one transaction, it contains a bunch of transactions. To understand / look at it easily, I've just stored a single transaction in every block. Let's say this is where Bitcoin started. This is the very first block of Bitcoin. And let's say person A and person B are the owners of Bitcoin, Satoshi Nakamoto. They have all the Bitcoin supply initially. Person A can send some BTC to person B. This is the first transaction that happened. It's on chain. Anyone can look at it. It will stay there forever. And then let's say the second transaction that happened on the Bitcoin blockchain was person B sent person C 5 Bitcoin, and then person B sent 5 Bitcoin to person C a bunch of times. If you add all of these transactions up, that is what makes the blockchain. Currently, we're at this particular block, and as time goes by, more and more blocks keep on getting mined. What is the benefit of doing this? The benefit of doing this is, number one, it's an open public ledger that anyone can look at. Number two, there are a bunch of miners throughout the world who are verifying this blockchain, making sure that every transaction there is legitimate. So you can at any point figure out what are the balances of a user. Every balance of a user can be reconciled by going back to the blockchain. If currently I say I own 5 Bitcoin, there is a history of blocks jahan pe I have received 5 Bitcoin for some people. It can be publicly verified by anyone. How do you know you have 40,000 rupees in your net banking account in HDFC, let's say? You see a bunch of transactions, right? What if those transactions change someday? HDFC Bank says you only have 20,000 rupees. Sorry, it just deletes one of your deposit transactions of 20,000 rupees. What will you do? You cannot do anything. Of course, this won't happen. Banks are highly regulated. This will not happen. But you cannot prove that. It is not a trustless system. You have to trust HDFC Bank, the engineers in HDFC Bank, and their relationship with the government. They would not do something this dumb to just delete some records so that they can decrease your balance and eat some of your money. On Bitcoin, on any blockchain, this is completely trustless. There is no single authority that is governing how much person do you have. If there is a very long blockchain that has happened, if this is the current final status of it, if at this point person B has 10 BTC and person C has 1000 BTC, this is all verified on a public ledger by many machines. If there is a new block that is added, if there is a new block that says person B sent person C 5 BTC, a bunch of miners all around the world verify this transaction, ensure that indeed person B correctly signed a transaction that said they wanted to send person C $500 or whatever 5 BTC, and only when let's say more than 50% or whatever the threshold is for that respective blockchain, only if more than 50%, 60%, 70% of the miners agree, is that block added to the blockchain. And slowly this blockchain becomes longer and longer. This is how blockchains work at a high level. I have a more detailed video on this. Top left, you'll find it. Click on it just to understand how blockchains work. You don't need to for this video. This video will not use blockchains. This is just the first solution that might come to mind. Start to store everything on the blockchain. You can create smart contracts on blockchain. Create an exam smart contract, store everything there. This use case is similar to, a lot of people build voting smart contracts. E-voting is one thing that, needs to happen in a decentralized fashion because votes are tampered from time to time. But again, there's a similar problem there. For 25 lakh people, solving 90 problems in 3 hours, we need to support around 20,000 transactions per second. If my math is right, could be wrong actually. I did this very quickly. But 20,000 transactions per second is a really big number. Most blockchains cannot support that. Blockchains are slow and blockchains require some gas fees. Whenever you're trying to make any transaction, you have to pay some gas fees. We need to make this faster, slightly more centralized. We need to create a faster, slightly more centralized blockchain where we get the benefits of having a almost publicly available set of blocks. Every question that the user submits is available for you to look at, but there's no real consensus. You need another way to verify that this transaction indeed was signed by person B. This transaction indeed this problem indeed was submitted by person A during a 3-hour window in a contest. You need to verify that, but you cannot have minors. The reason blockchains are so slow is because of consensus. All of these minors arriving at the consensus कि हाँ भाई this transaction is indeed correct is what takes a lot of time, which is why you cannot have multiple minors. We're not building a blockchain here, as at least a decentralized blockchain. We're still trying to create, a queue of a bunch of elements where every element in a queue is like the submission that a user made, but we're not doing any consensus on top. Let me elaborate on this a little bit. What we're trying to make is a verifiable state machine. When a database-backed service is hosted on an untrusted infrastructure, which has been our assumption throughout. If you're storing it on AWS, it's untrusted. If you're storing it on Azure, it's untrusted. How can the service provider, how can NEET NTA prove to its client that it's operating according to a predefined specification? What is the specification for an exam website? Okay, users will come, they will be submitting an application or like a bunch of answers during a 3-hour window, and only those 3 hours of submissions will be used to calculate their final results / ranks. This is the specification that a server like this needs to follow. How can it prove after the examination it indeed did this, and every submission that's in there was done by a user, even if the database is tampered, even if the backend is tampered, even if the Amazon AWS servers are, being shady for whatever reason? How can it still prove that हाँ भाई, these submissions were indeed made by these users, and there's nothing shady happening in the middle? What are the problems we're trying to solve for? Ensure the submission was made by the student and no relative. ऐसा नहीं कि after the contest happened, few hours later there is a rogue entry in the database, or even during the contest there is a rogue entry in the database कि हाँ भाई, this problem is being solved for this user by some relative of that specific user who works at NTA. No. Ensure it was made every submission was made in the time window of 9 to 12. After that, if there is any submission, it should be discarded / avoided / there's something shady happening. Users can verify their ranks by finding the submissions of everyone and calculating their marks. This is the main point to consider. The biggest problem right now is there's a tussle between both the sides and no one can verify. If someone could just verify that their rank is indeed correct, that indeed in that 3-hour window there were X number of people that performed better than them, then there won't be any problem. And if there is a problem, then you clearly know that there were grace marks given, or some other way that some other user was pushed up the chain. How can you verify your rank after the examination is done? By creating a verifiable state machine. Let's see what that means. Let's say this is our exam backend, where as the students come and the 9 a.m. deadline comes, people start to submit problems here. For example, if student 1 is making a submission, they send a submission to the exam backend that looks like this. Okay, hey, for problem ID 1, I think answer that I'm trying to submit is B. And the exam backend doesn't store it in a database, doesn't calculate if it's right or wrong, doesn't assign a score to the user. The backend simply pushes this onto a queue. If there is a second user that sends their submission, that also gets pushed onto the queue. By the end of it, you have a very long queue of time-stamped events that these students sent, each event being what was the submission that this user made at this specific timestamp. Once you have this very long queue of events that happened in a span of three hours, you can create verifiers, which will take all of these events, calculate the scores for individual users, and then can eventually calculate the rank. Where is verification here, 𝗥𝗲𝗃𝗏? This looks like a very simple Web2 problem. You could have just stored things in a database. What's the point of storing it in a queue? And the answer is, this queue can actually be made public. You don't have to make it public. A government / the NTA, whoever is the testing agency, can decide to keep it private. But in case a lot of questions are being asked, they can always make this public so that the users can themselves verify कि हाँ भाई, indeed these were the timestamp of events that happened that led to me reaching a certain point. There are a lot of inconsistencies in this that we will fix eventually. But this is a good start of how people can verify. You can either keep this queue completely public so that people can look and check indeed the person who has rank 1 has 90 submissions, all of them are correct, that led to them reaching 720 out of 720, and then anyone can verify the same thing. In case you make it public, anyone can verify. In case you make it private, you do keep it private, you should have multiple result calculators which individually check, all of these being pretty separate, and then all of them eventually reaching consensus ki rank 1 is X, rank 2 is Y, so on and so forth. There shouldn't be a single result calculator, because again you can have some logic in here that takes these events but changes the rank of a single user by a bit. So have multiple result calculators if this is a private blockchain or queue that you're maintaining, and as long as all of them, or sufficient amount of these calculators are able to reach consensus, they're all saying rank 1 is person A, rank 2 is person B, so on and so forth, you can finalize that as the final list of winners. If you do make it public, then even a single result calculator is fine, because someone out in the world will run a similar calculator, and if something is wrong, they'll report and let you know. Should you make it public or private? Depends on how transparent you want to be. 𝗰𝗲𝗿𝗀𝗀, if you're making this public, why not just make the database public? Why even a queue? Just maintain a database where you put all the entries and make that public. Yes, you can maintain a database as well. The key thing is every submission by this user should be over here. It should be completely verifiable. Okay, what all submissions they made, at what timestamp was that submission made. How can you ensure that all the submissions that you see were indeed made by this user and during the contest? Do you think this point is solved now? I've created a queue. Anyone can verify. Let's say this queue is public. Government kept it public right from 9 a.m. only. Anyone out in the world could see the submissions of any user. It's almost like posting data on a public blockchain like Ethereum or Solana. Is this problem solved? The answer is no. As I said, you cannot trust anyone, including the exam backend. What if student 2 sent some data, but the exam backend changed it before sending it onto the queue? What if the exam backend has been written by a developer whose brother is giving NEET this year? So that guy, put some malware in here to either prevent other users' submissions from going in, or, put extra submissions for his own brother that he felt was right. Some malware he put and was able to solve the problem. Basically fill up the queue anonymously. The server was able to add things to the queue that were not sent by any of these end users. We need to be able to catch these. Whenever there is an extra entry that's added here that is not by an end user, we should be able to catch that. How can you do that? We want to prove to a server that this message indeed came from the student. Every message that is here should come from the student. The central authority should not be adding an extra entry here and wasn't tampered by someone in the middle. You can do this by using public key cryptography. I will repeat the problem. We have a very nice public queue. If it's made public, anyone can verify. The only problem is all the submissions here will have problem ID, answer, and maybe the user ID here as well. The problem is, these submissions can be made by a centralized AWS server. This AWS server might have code written by a developer that's just taking the submissions from a user and putting it here, but might have some extra code for their friend to, put submissions on their behalf. How can you make sure this student directly talks here and every submission that's here came indeed from this specific student? How can you prove that? By using public key cryptography. What is public key cryptography here, 𝗤𝗲𝗃? Let's understand this from an example. Fairly common example. Let's say you're a terrorist. Maybe not as common, but bear with me for 5 minutes. You want to send a message to the world. How would you do this? Conventionally, whenever a terrorist wants to send a message and you want to be sure they have sent it, they usually make a video, right? They will make a video where they'll have some timestamp in their hand. Okay, today is XYZ date and we're going to do some certain attack, and that creates panic in the world. Okay, bhai, he really came on video. That means he's really the one who has put out this message. It's not a fabricated message from media. But rather than doing, let's say you cannot do that. You cannot put out a video. The terrorist is too shy to put out a video. But anyone who gets this message should be able to verify it came from you. The terrorist, a lot of random news can come out, right? How can you verify it indeed came from, let's say, a certain terrorist? Either they create a video and the video goes out, most probably, it is the terrorist and, it's not an AI generated video. Or you can use public key cryptography. This is how the terrorist would make this information news public by using public key cryptography. Number one, the terrorist will generate a public key and a private key. When you're doing public key cryptography, this is very similar to encryption. When we were doing encryption, we encrypted a message using a secret. We decrypted the message using the same secret. That's called symmetric encryption. What we are doing here is asymmetric. We want if a terrorist generates a public key and a private key, that might look something like this. The terrorist broadcasts their public key to the world. Just one time. One time the terrorist has to come on video and say, this is my public key. Any future message that I send will be signed by the private key of this public key. I repeat, the terrorist first generates a public private key pair. This is a very common thing that happens. Okay, you generate two keys. One is like your username and password for your HDFC bank. Your username you tell to the world, okay, my name is 𝗥𝗲𝗄𝗏. Everyone should know this. This is my username on HDFC bank. For that, once you have to, prove to the world that you indeed own this public key, you can come on video and say it. Once you've done that, no longer do you have to come on video. Now, you have to simply sign the message that you're saying using your private key. I repeat, what did you generate? You generated a key pair. You generated a public key and a private key. The algorithm that you used to generate this public key and private key clearly states, if there is any text message that you want to send out to the world, sign that message using your private key. I repeat, let's say the terrorist wants to send out a message that says, I will be attacking XYZ country tomorrow. They can sign this message using the private key that they had. And that will spit out some gibberish like this. Some signature like this. This signature and the original message, if they give out in the world, right, they don't have to create a video. They just have to send out, ye raha mera message. This is my message. And this is the signature that clearly states that this message came from me. How does this signature state that the message came from them, 𝗥𝗲𝗄𝗏? Because we are doing public key cryptography. Anyone can verify that the message indeed came from that user using their public key. The terrorist had broadcasted their public key to the world बहुत पहले. Few years ago, he came out and said, ये रही मेरी public key. This is my public key. Everyone knows it. Now, anytime he signs a message using their private key that they did not expose to anyone, their private key is only with them. Their public key is with everyone. Their private key is only with them. The terrorist signs a message using their own private key, and then anyone can verify their message using the user's public key. The terrorist, what message did the terrorist take out? This one. This message has been broadcasted to the world. Anyone can take this message and verify, this message did indeed come from this public key. You can either get a tick or a cross on this public key. If you get a tick, indeed this message was signed by the terrorist. So what is public key cryptography? Public key cryptography states, if you ever want to, it does two things. This is one thing it does. It also does another thing. Let me quickly share. Step one was, anyone who wants to do communication to the world, first create a public key, private key pair. Basically create two strings like this. This is your public key, let's say, and this is your private key. The same thing is true for crypto wallets as well. If I open any one of my wallets over here, you will see the wallet has a public key. This thing right here, that's my public key. If I copy this whole thing, it's a very long string. It also has a private key that if I want, I can go to my settings and export. Public key I share with everyone. This public key I can share with everyone. Private key I don't share with anyone. If I share my private key, you can get access to these $3,700 that are present here. Similarly, this isn't a crypto public private key pair. This is a standard public private key that the terrorist created. And this public key was given out in the world. Now, if the terrorist ever wants to send a message, they can sign that message using their private key. They can take this private key And whatever message they want to send out to the world, let's say, I will kill you. They will send out not just the message, they will send out this message, this is my message, and they will say, okay, this is my signature. The signature came out from this text plus this private key, some algorithm that takes this text and the private key spits out some signature. This text and signature block, anyone can now use and verify कि यार हाँ इस बंदे की public key तो यही थी. Few years ago he came on video, he told us, sorry, the private key was this and the public key is this. Few years ago he came on video and told us this is their public key, and I could indeed verify that given this text, it was indeed signed by the private key of this public key. I repeat, check mark. Anyone in the world can verify कि यार ये जो public key आई थी ना, whenever I run this signature by this public key, indeed I will kill you comes out, which means this message, this gibberish, this signature was indeed signed by the private key that only the terrorist has. Hence, you know that the terrorist is the person who gave out or signed this specific message. This is how you can prove to the world again and again, okay, you know, I am sending out this message. This is true in the other direction as well. Okay, if I ever want to create a message and send it to a terrorist, and I want to make sure कि सिर्फ terrorist ही उसको पढ़ पाए, only the terrorist is able to read it, I can write my message. For example, my message can be bring world peace. This is my message I want to send to the terrorist, and I want to be sure कि सिर्फ terrorist ही इसे पढ़ पाए, only the terrorist is able to understand it. I can sign this message using the public key of the terrorist, which is, you know, this thing right here. I can sign this message using the public key. It will spit out some gibberish that I can somehow hope it reaches the terrorist. Let's say the gibberish did reach the terrorist. The terrorist can decode this message using their private key, and only the terrorist can decode this message. No one else in the world can. So you can do this both sides. A terrorist can lock something using their private key and other people can unlock it using their public key, or someone in the world can lock something using their public key and then the terrorist can unlock it using their private key and understand it. उल्टी direction में क्या हो रहा है कि this message once signed, only the terrorist can understand, no one else can. Forward direction में what was happening कि anyone in the world can read the message, that is fine, but there is a signature along with it. It indeed came from this user. All right, let's look at the code really quickly. If you want to, you know, create a very quick public private key pair and, you know, sign a message, share it with a friend. As I showed, whenever you have a Solana wallet, you have a public and a private key for it. That public private key pair also follows an algorithm called the ED25519. That's one of many algorithms that let you create key pairs that follow these formats. So you can just use this library. You can also, you know, use the crypto library, create one from scratch. Either is fine. You can generate a fresh key pair using the keypair.generate function here. It will give you both a public and a private key. Then this is the message that, let's say, you're trying to sign. You decode this message into bytes by using the decode UTF-8 function that comes from TweetNACL. This is a common library that's used for, you know, a bunch of cryptography stuff. Finally, you sign the message. You sign the message using the secret of the key pair. Log the message just for kicks, see what it looks like. And then eventually the other side can eventually verify your signature, the message that you're trying to send, with the public key of your key pair. The public key is something you publicize. The message as well as the signature is something you publicize. And then anyone can come and verify, okay, is this indeed a message? And that was sent by, you know, the terrorist in this case. Was it signed by the terrorist? Let's try to run this code really quickly. You will see the final thing that gets printed is true, which means it was indeed, we were able to verify that this was signed by this public key. And if you look at the signature, how was it created? It was created by signing the message using the secret of the key pair. Why are we talking about public key cryptography? Because what do we want? We want if there is a student that's sending a message and it's eventually being stored in this queue, the verifiers should be able to verify it indeed came from someone that has that private key. If this private key is generated outside of the exam backend, if the exam backend does not have access to this private key, then any message that the exam backend sends itself, it will not be able to sign on behalf of student 1. If the terrorist has the private key, only the terrorist can take out the message to the world, right? No random media agency can sign on their behalf. Whoever has the private key will be the person who will be able to sign the message and broadcast it to the world. There are some inconsistencies here as well that we'll discuss towards the end in the last slide. But now, when a user wants to send a message, they will not simply send the message in plain text to the exam backend and the exam backend will send it here. No. They will first sign this message using their private key. Every student will, to begin with, create a public and a private key. When you reach the examination center, click on your I want to give this examination terms and conditions button, a public and a private key is generated for you. And every message that you send first needs to be signed by your public key and only then, private key, and only then will you forward it to the backend. The backend cannot tamper it anymore. Whatever message you have written, this is your signature. This message was signed using your private key. The exam backend can try to change it, but even if it does, that message will not be verified over here. So if they try to write their own events or they try to tamper yours, that event will become invalid if they try to tamper it. We'll discuss a little bit how you can fix that as well in the end. But if they cannot initiate messages on behalf of any other user now. Every user has their own private key. Only the user can create a private message that eventually reaches the blockchain or whatever, your queue in this case. And by the end, you have a queue that looks like this. It has a bunch of signatures along with the original message, along with the public key of the user that, signed the message. So that whenever verification happens eventually, whoever is trying to verify all the events clearly is able to tell that this was student 2, this was student 1 based on their public key, and can also verify that indeed this message came from user 1 because this message over here or the signature over here can be decoded using the public key that's mentioned here. That is how you can ensure that there cannot be any man in the middle attack. If there is a man in the middle, they will not be able to talk on behalf of any of these students. The result calculators eventually will also pick things up from here, and this time they can be sure that no one put any erroneous data in there. There was a 3-hour window in which a bunch of submissions happened. They got picked up by these result calculators. The public ledger can be frozen right after the contest. It's available for everyone to verify their marks as well as other people's marks. If you want to verify, if you feel like you have 630 marks, yet your rank is 50,000, which is something that did not happen until a year ago, you can just go to this public ledger or this public queue, start to process all the messages, and you'll find the exact number of people that are ahead of you. That's exactly your rank, or that should be your rank. There are still inconsistencies here, but most of the problems are solved. The last thing that we were talking about during context phase, how can you ensure that all the submissions that you see were indeed made by this user during the contest and not added later? All the submissions were made during the contest and not added later. If your ledger is public, during the 3-hour window, people can verify all the submissions that are coming in, lock the ledger at the end of the 3-hour mark, and every submission over here is signed by the user. Every submission is signed using a private key, and hence you can verify it. It wasn't added by another user. This private key strictly exists on the computer on which the user is sitting, and hence every message is signed. Now, Harkira, what if I take this private key and send it to my mama back home and she can solve for me? Yes, you can do that for cookies. Of course, there will be firewall rules. Only the college laptops that you're sitting on can only talk to exam backend. Else you can just Google questions as well, right? You can send questions to your mama on WhatsApp as well, right? So you'll have some sort of a firewall rule. When the student is sitting, they're only allowed to talk to this backend and no other backend they can talk to, and hence they can't share their private key. Their private key is strictly restricted on their laptop / computer that they're sitting and giving the examination on. These two problems are solved. These are the during contest problems. The after contest problems are also fairly simple. All of them are solved now. If you follow this architecture, basically results can be given out immediately. If all the ledger is present publicly, users can just calculate their own results. People getting grace marks, this data not being public. Now to bhaiya, all the submissions are public. This queue is public. Now if you want to add something on top of it, grace marks or whatever, you will have to put them on chain. If you create a new ranking system, if you increase the marks of any specific question, let's say if a specific question gets tainted or removed, or there are two options, any of these changes happen, they need to be broadcasted everywhere. Everyone needs to know. Whoever is calculating the result will then add those grace marks and recalculate the result. So you cannot hide the fact that you're changing / adding grace marks. All the submissions that the user made during the 3 hours of the examination are public, verified, signed, and hence you can recreate the leaderboard. If there is something extra you're giving on top, you will have to broadcast it, else your result and the publicly available result calculator's result will be very different. Ranks marks can be modified. As you saw, you cannot modify them anymore. The student has a private key. The student is signing using it, unless they're able to somehow sneak out their private key, which, is it possible if they have a phone that has internet? Sure. But if you have a phone that has internet, you can do a lot of other things like Google questions. I would assume invigilators are smart enough to not allow that. And, the user is also not smart enough to find their private key somewhere in the browser and, figure out, this is a private key that I need to send to my mama back home who will solve questions for me. No way to verify my rank / number of people that are actually ahead of me. This can be done now, right? You have a public ledger. That public ledger has all the details. As long as you have enough compute to, calculate all the submissions, you can create the final leaderboard on your side. Privacy issues because you can scrape the data. Now, everything is public. There are privacy issues on another level, but at the same time, the public key doesn't associate to a user right now. What are we storing? We're storing the messages and the public key. We are not storing their parents' information, their address, things like these. And hence, even though yes, data is public, there are privacy concerns. You don't really know the identity of the user. Right now, what happens in the result website is you can literally pull out the identity of a user. You can literally, see their parents' names, address, center, things like these. Here, you can just see a public key, which is fine. You don't know what the public key to identity association is. That, can be stored in a safe central server. So it's not a privacy issue as such. That's pretty much it. You might ask the question of Arkirat, if, as I just said, public key is the only thing we store here. So how do you associate the public key to the real user and, their enrollment number, things like these? The answer is, when the student comes on the website and clicks on the start button, there's an invigilator there, a certain computer has been assigned to them. There is their enrollment number written over here. The very first event that they send to the server can look something like this. Now, this isn't great again. If you put their enrollment number on chain, that means anyone can see their enrollment number. That means they can see this was the performance of enrollment number 11441231. It's mostly fine if this enrollment number's performance is public. It's anyways going to be public. Everyone knows rank 1 was, Mahindra Pratap, let's say, or, this enrollment number. As long as this cannot be associated to their parents' name, address, it's fine. And, this way you can ensure, in every future request, the user only sends their public key. But the very first message they're sending, they can associate their public key and, their enrollment ID. That's pretty much it. There are still a bunch of open questions. Let's talk a bit about them. Okay, what if the user sends a fake private key that they've shared with their friend? This is a good one. Okay, what did we say? When the user comes, they will have a public private key over here, using which they'll be sending all the messages or, signing all the messages. What if as soon as I come to my laptop, I quickly change this private key to a private key that I've already shared with my friend who's sitting at home? Then that friend can solve for me sitting from home. That friend can talk to this exam backend server. Few things you can do here. Number one, this private key generation can have some sort of a prefix. Every public key that you create, you can grind a public key. By grinding, I mean, if the public key usually looks fairly random, let's say the public key looks like this, you can grind it to ensure it has a certain prefix. For example, Maharashtra center or something like that. Or center ID is the first 4 letters over here. That way, you can't really guess before coming to the center what your prefix might be. And if you try to update the private key that you've already shared with your friend, it will not follow the same format, and you can, find out that this user updated the private key. Other thing can be, only the invigilator gets the option of starting. There's a refresh private key button here. The invigilator comes, refreshes the private key, and only the invigilator starts the examination, which sends out the event and associates the user's enrollment number with their public key, so that they can't really update it in their browser and hope whatever private key they've sent to their friend is the one that can be used here. So these are just these are just edge cases I've thought of. I'm sure there are more edge cases that might be there, but hopefully there are solutions to those edge cases. Another edge case was, what if a central server doesn't send a particular user's message to the queue? What if central user can no longer fake messages? The central server can no longer fake messages, but it can stop messages, right? What if it starts to stop messages for a certain student? He might think, yeah, AR1 at this time, but this person might be AR1. I'm going to stop all of his messages from going to the queue. How can you fix this problem? There are a few ways here. When the user clicks on the submit button, they shouldn't immediately, if the request reaches the exam backend, that does not mean their submission has happened. If it reaches this queue and there is a processor that's processing this queue, if that processor talks to them, only then should they move the user to the next problem. I repeat, this is exactly how it happens in exchanges. If you're ever building an exchange and placing a limit order, market order, or putting something on the book, you send a request to a server. The server sends it onto a queue. This is your queue of all the events that have happened since forever, that you usually give to auditors in case an auditor comes and wants to check, make sure you're doing things on the up and up, and you're not modifying balances in your databases. From here, it gets picked up from a processor, which then responds back to the user and tells them your order has been placed. Similar thing might need to happen here. Okay, you send a request to a backend, goes to a queue, gets picked by a processor, and the processor lets you know your submission has happened. Only then do you move the student to the next problem. Else the user, sort of stays stuck on the same problem. And if their submission doesn't go through for 2-3 times, they can just call in a invigilator and go from there. That's how I would solve the second problem. Another edge case that I thought of was, what if the central server itself starts to fake sending requests with the private key for an enrollment ID? Literal man in the middle attack. Okay, this server, whoever this guy owns this server, their cousin is, let's say, this guy. They tell their cousin, bhai kuch mat kariyo. Don't do anything once you reach the examination center. I will make submissions on your behalf, including the very first, result over here. I will send your enrollment ID and then I'll solve all the problems for you. Here again, you can grind the public key for the user. You can make sure the public key prefix is only known at the venue. You can ensure that if you have some sort of attendance, if this user did not come, then this user did not attend, all their submissions have happened via backend. If the user did come, you make sure you send out a message, you click on the start button, so this user starts their session. And if the backend starts another session with their own private key, there are conflicting sessions for the same enrollment ID. Something shady is happening. 2 computers are trying to submit for the same user, things like these. So there will be more such edge cases that you might have to worry about. If you thought of more, let me know. I've tried to decentralize this mildly. This problem can be, you can totally decentralize this. You can create your own blockchain, have anyone become a miner, and, have a truly decentralized examination. The only problem is blockchains aren't, fast enough to handle 50,000, 100,000 transactions per second, which might be the throughput that needs to be supported here. Only a central system can support that, unfortunately. Queues can support that kind of a throughput, so can a server or a distributed server. But blockchains with consensus cannot. So you have to build a mildly decentralized system. What we've built here is very close to a blockchain. A blockchain is nothing but, a bunch of blocks where you put on a message and sign it using a private key. That's almost exactly what's happening here. The only thing that's not happening is consensus. There is eventual consensus. Once the contest happens, a bunch of, result calculators can start and arrive at consensus whether or not the final ranking looks a certain way. But during the contest, there's no consensus that is happening. You're just shoving all the inputs that come from users onto a queue. That's more or less what, a blockchain is. All right, with that, light bhi chali gayi, guys. This is all I had for this video. Let me know if you understood the architecture. As I said, this is fairly common architecture. A lot of centralized exchanges are built in a very similar fashion because they need to be centralized, because they need to be very fast. But at the same time, you need to be able to prove that a certain user's balance is indeed X. If they've played, thousands of orders in the history of years trading on your centralized exchange, you should always be able to arrive at their final balance given, a bunch of their history of transactions they have done over the years. And each one of these is usually signed using a temporary private key that you give them through an MPC cluster. Now, what is an MPC cluster? Basically, private key generation needs to happen a certain way. Never mind, let's not go there. But yeah, that's a brief of, the architecture. A lot of this architecture was actually inspired by CEXs or centralized exchanges because they solve a similar problem. With that, I think we can end it, guys. I will see you guys in the next one. Bye-bye.